All right, hello everyone. We're going to be going over section 6.1 for this lecture. So 6.1 is on angles, arc length, and circular motion. We have 6 objectives, which are going to be our first objective, angles in degree measure. Number 2, convert between decimal degree, minute, second, measures for angles. 3, find the length of an arc of a circle. 4, convert from degrees to radians and from radians to degrees. And 5, find the area of a sector of a circle. And lastly, 6, find the linear speed of an object traveling in circular motion. So, too zoomed in. All right. So objective 1, we have angles in degree measure first. So a ray or half line is a portion of a line that starts at point V on the line and then extends indefinitely in one direction or the other. So if we look at our image here, we have our number line or just a line in general. We have our point V, which is defined, and then we have our highlighted blue line that ends in an arrow that is going off to the right. So this is going to be considered our ray. Our ray can go in the direction of right or left. It doesn't matter, just in one direction. So the starting point of a ray is called the vertex. So V in this case is going to be the vertex of this ray. So then, when two rays are drawn with a common vertex, they form an angle. So this means that if we have our ray here, and if we just drew in another line going this way, let's imagine it's a little bit bigger. If we had a line going that way, we see that they would form an angle. So this portion right here would be an angle. So when they're drawn with a common vertex, they form an angle. So you would draw another line extending out from the vertex, and then you would have an angle between those two lines. We call one ray of an angle the initial side and the other the terminal side. If the rotation is in the counterclockwise direction, your angle is positive. So this is moving from your initial side to the terminal side when you draw, that arrow. If you're going in the counterclockwise direction, it's positive. And if you're going in the clockwise direction, it's going to end up being negative. So here we have some examples. So for picture A, here we have our initial side, and typically what's going to happen is your initial side is going to be the horizontal ray. It's going to be whichever one that's lying horizontally. Your terminal side is going to be that one that has any other kind of different angle to it. So in our first picture, we have our initial side, which is horizontal. Then we have our terminal side, which is a little bit higher up. And then we have this angle, which we're calling alpha. That's the Greek letter for alpha. So we see we're going in the counterclockwise rotation. We're moving in this direction, so we're counterclockwise, which means that it has a positive angle. For B, for our next image here, we see we have the exact same array set up. We have the same initial side and terminal side, but instead we've gone in the clockwise direction with our angle, which we labeled beta. So in this case, even though we have the same setup with our rays connecting to our vertex, since we had our angle going in the other direction, this means that we have a negative angle. Then, starting over again, we have the same setup here with our terminal and initial sides connecting to the vertex. And instead now, we've completely gone through the terminal side to come back around through the terminal side. But what we see here is that we still went in the counterclockwise direction, even though we went all the way around. So it was still in the counterclockwise direction, which means that it is going to be positive, that symbol, which is gamma there. So as a note, when we write alpha, beta, gamma, or in most cases, theta, these are Greek symbols that are often depicted angles, and they're not equal to each other. It's very simple to see here that they aren't equal to each other because we see that there is a difference in how many times that they are going around or what portions that they're actually going around, but just to make that clear. So we'll most commonly call our angles theta. So an angle theta is said to be in standard position if its vertex is at the origin of a rectangular coordinate system and its initial side coincides with the positive x-axis. This just means if you see an x and y plane, or where you have your y graph and your y-axis and your x-axis. If you see this, this just means that your initial side is going to lie on the x-axis and the positive direction. So this is what we mean by positive direction. Our initial side we see is lying here in the positive side of our x-axis. They're connected at the origin, so the vertex is the origin, and this terminal side we see is just going to be pointing in whatever direction. So our terminal side is moving a lot. Our initial side is going to be stuck on that positive end of our x-axis. So we've took what we just learned, and we're just now placing these rays with kind of connected vertex. We're just placing this on top of our XY graph. So we've placed it on top. So same things as before. Theta is going to be in standard position in both of these images here, since we see that our initial side is lying on our positive part of our x-axis, and our terminal side is pointing in whatever directions. So it is in standard position. We see that in our first image, though, we are going in that counterclockwise direction, which meaning that we have theta as positive. Then in our second graph, we do see we are moving in the clockwise direction, which means that theta is going to be negative. So when an angle theta is in standard position, either the terminal side will lie in a quadrant, in which case we say that theta lies in a quadrant, or the terminal side will lie on the x-axis or the y-axis, in which case we say that theta is a quadrantal angle. So this just meaning that our terminal side can lie on any one of the axes. This means that we can end up with an angle that looks like a right triangle without the hypotenuse, or it can be a straight line, or same thing, but the other direction. Or they can both lie on the positive part of the x-axis, which would just make it look like one single ray. So this just means that if we had anything in between, if our terminal side laid anywhere in between our axes, this means that we're saying that theta lies in a certain quadrant. So we separate out our XY graphs as quadrants. So quadrant 1 would be the upper right-hand quadrant, quadrant 2, upper left, quadrant 3, lower left, quadrant 4, lower right. So in any case, whenever we have our terminal side not on an axis, we're just saying that theta lies in a specific quadrant. So we'd say, oh, theta is in quadrant 1, or theta is in quadrant 2, or something like that. It's whichever side your terminal side is ending in. So for example, in our first graph here, graph A, we see that theta lies in quadrant 2. Our terminal side is in or ending in quadrant 2, which means that that is where we're saying theta lies. Then in graph B, we've gone now into a different quadrant. So we see our terminal side is in quadrant 4, which means that theta is in quadrant 4. Theta in this case is also negative because we're going in that clockwise direction. Then lastly, graph C, we see that theta is a quadrantal angle. That just means that our terminal side is lying on an axis. So whether it be the X or Y axis, we say theta is a quadrantal angle. This is because if it's lying directly on the axis, we can't say what quadrant it's in because it's on an axis, which acts as the barrier between the two quadrants. So it's either in a quadrant or it's not in a quadrant. So you're either stating whether it's in one of the quadrants or you're stating that it's a quadrantal angle. It's one or the other. So as a side note, the two common units of measurement for angles are going to be in degrees and radians. So when we measure theta, we would say theta is blank degrees or blank radians. This is something that we're going to go over a lot more in the next few sections. So an angle's full rotation in the counterclockwise direction is measured at 360 degrees, or the way we write it is the 360 with that little circle there at the end. but we do say 360 degrees when we're just saying it. So 1 degree is 1 divided by 360 of a revolution. So it's 1/360th of a revolution. 1 revolution is just how long it takes to get around the circle 1 full time. So a right angle is an angle that measures 90 degrees or 1/4 of a revolution. A straight angle is an angle that measures 180 degrees or 1/2 of a revolution. So in our pictures here, A, B, and C, for our first part A, our terminal side and our initial side are both lying on the positive x-axis. So they look like it's just one ray. So in this case, we would have 1 whole revolution. And it's in the counterclockwise direction, so 360 degrees. Then for part B, our terminal side is lying on the positive y-axis. So we get a right angle, which tells us that we have 1/4 of a revolution in the counterclockwise direction, meaning that it's going to be 90 degrees. Then lastly for C, we have a straight angle. We call it a straight angle because it looks like a straight line. It's just going across, it's going to cover all of the x-axis. So this is going to be 1/2 of a revolution. We've gone around half of the circle. So 1/2 revolution counterclockwise, so it's positive, and it's a positive 180 degrees. So in our first example, we want to draw the angle 210 degrees in standard position. So if we're drawing this in standard position, we have our graph here, and we're going to zoom out a little bit. We have our graph here. This is our x-axis. This is our y-axis. If we want it in standard position, this means that our initial side has to lie on the positive part of the x-axis. So let's go ahead. This is our vertex. We'll label it V. And our initial side will lie here. This is our initial side. Now we need to determine where our terminal side is going to lie. We need our angle to be 210 degrees in the standard position. If we think about the number 210, we know that 180 degrees looks like a straight line. If we subtract 180 degrees from 210, so as a side note, 210 minus 180 is going to come out to 30. So what's going to happen here is that we are going to go 180 degrees plus 30. So when we draw this, we say we know that this is 180 degrees. And now we need to estimate an extra 30. And this is pure estimation. We're just drawing it out. So we're just going to estimate what another 30 degrees would be. Since we know that this is a full 180, 30 would be about 1/6 of this area. So it's going to be 1/3 of a quadrant. So we're going to go ahead and just say that this is going to be about 30. So we're adding this. 180 plus 30 is going to be about there. So we'll state that, and we'll actually move this V over a little bit so it's on the way. So we're going to say our terminal side will look something like that. So it's not quite halfway, but it's 30%, or it's 30 degrees. So not quite halfway, but a little bit less. So our angle 210 in our standard position will look a little bit something like this, where if we did draw all the way around, that would be 210 degrees. So we picked our values. We went with something that we knew already. We know that 180 degrees would be the full half rotation. So since we knew it was a half rotation, we just had to estimate the extra that was added on. So the extra, we estimated that extra 30 degrees. So whenever you're going to be measuring out a specific angle degree in standard position and you don't know the exact placement, that's what you're going to want to do. You have to use what you already know and estimate the rest. Also, at any time that we do examples, I fully encourage you to pause the video right before I go through the solution, and then you can go ahead and see if you can do it on your own, and then maybe watch through my solution. Just a suggestion. All right, so on to objective 2. We want to convert between decimal and degree, minute, second measurements for angles. So we can obtain subdivisions of a degree in decimals, minutes, or seconds. 1 minute, which we then signify by writing 1 with an apostrophe, is defined as a 60th of a degree, 1 divided by 60. And 1 second, which we'll write as 1 with 2 apostrophes, is defined as 1/60th of a minute, would end up being 1/3600th of a degree. So for an example, an angle of 30 degrees, 40 minutes, 10 seconds would look like 30 degrees, 4 minutes, 10 seconds, where we have 30 with the little circle, 40 with an apostrophe, 10 with 2 apostrophes. So when we write this out, we write this as degree, minute, second. So it's going to be in decreasing order. So 1 revolution, counterclockwise revolution, that's 360 degrees. 1 degree would be 60 minutes. 1 minute is 60 seconds. So there's some conversion that you can do there between your degrees, minutes, and seconds. A central angle is a positive angle whose vertex is at the center of a circle. If the radius of the circle is r and the length of the arc subtended by the central angle is also r, then the measure of the angle is in 1 radian. So as we detailed earlier, your angle can be measured in radians or degrees. So this is just kind of stating how we get radians. So if we have a circle here, which we're going to focus first on our one on our left, we have a circle. We're stating that its angle is 1 radian. And so the radius of our circle is r. So this means that our arc length is also going to be r. So we have a terminal initial side. Then on our right-hand side, if we draw a larger circle, this means that we have 1 radian because we still can consider the smaller circle being on the inside, while now our new radius is 3 and our arc length is also 3. So this would still be considered 1 radian. So objective 3, we want to find the length of an arc of a circle. So we have figure 11 here, and we see we have 2 angle measurements, theta and theta 1. Theta is going to correspond to the arc length S. Theta 1 corresponds to the arc length S1. So from figure 11, the ratio of theta and theta 1 are equal to the ratio of S and S1. So we see here that ratio written below our image. Then if we let theta 1 be equal to 1 radian, then S1 is equal to the radius r, and we end up getting our equation for arc length. So for a circle of radius r, a central angle of theta radians subtends an arc whose length s is going to be s is equal to radius times theta, where in this case we're going to be measuring theta in radians, not degrees. So this tells us our arc length. So this is our equation for our arc length. Everything before was just theorizing how we got here. But this is our equation. Theta is measured in degrees or radians, but in this case, we're really focusing on the radians. So we're actually going to cross out degrees. It's measured in radians for the purpose of finding arc length. Let's go ahead and do an example. We want to find the length of an arc of a circle whose radius is 4 meters, subtended by a central angle of 0.25 radians. We're looking for the length of an arc. So we're using the equation for arc length. So really the only thing that we're focusing on is we're focusing on the radius and theta. Those are the only things that we need to find the length of the arc. So we know that our equation for arc length is S is equal to radius times theta. Where now we have that radius, which we write in as R, is equal to 4 meters, and theta is 0.25 radians. So if we have our radius and we have theta, we just need to multiply them to find our arc length. So S is going to be equal to 4 times 0.25. 0.25 is the same thing saying 1/4, so 4 times 1/4 is going to end up giving us 1. And since we're finding length, we're looking at 1 meter. So our arc length in this case would be 1 meter. So using that equation, it's fairly straightforward to find the arc length as long as you have the radius and your theta measurement in radians.